4-5, writing a function rule. So in the last section, we were graphing function rules. In this section, we're going to learn how to write equations that represents functions. Okay, and that's our objective for this section. Essential understanding is many real-world functional relationships can be represented by equations. And we can use an equation to find the solution of a given real-world problem. Okay, so primarily, this section is gonna consist of some sort of word problem, some sort of real-world situation that we're gonna have to look at and try to turn it into a math equation. We'll go through a couple examples like every section, but the trick to this section is that every question is slightly different. You just have to read it and figure out what exactly is going on. So our first problem. We can estimate the temperature by counting the number of chirps of the snowy tree cricket. The outdoor temperature is about 40 degrees Fahrenheit more than 1/4 of the number of chirps the cricket makes in 1 minute. What is a function rule that represents the relationship? Okay, so we have a couple of variables that we need to define. Okay, first, we have some sort of temperature, right? So we know the temperature. That's going to have something. So let's use a variable t is temperature. And we have number of chirps that this cricket makes. So let's use n for number. So that's going to be the number of cricket chirps in 1 minute, right? Because that's what it says right here. All right, so what's happening here? Okay, so the outdoor temperature is about 40 degrees more than, okay? So the temperature is gonna be, right? The outdoor temperature is. So when you see the word is, that's usually gonna be a place where we should put our equal sign because we're saying this is equal to this. So let's start with 40. 40 degrees more than, so that means we are going to be going up. So we want to add 1/4 the number of chirps. So 1/4 times n. And that is my function rule. Does it fit with what this is saying? 40 temperature is 40 degrees more than this. So we're going to start there and we're going to add 40 to it. Okay. So we could also have written this function rule like and add 40 degrees to it. Either way, doesn't matter, as addition is commutative, so we can do that either way we want. Okay, let's try another one, our got it problem. So, a landfill has 50,000 tons of waste in it. Each month, it accumulates an average of 420 more tons of waste. What is a function rule that represents total amount of waste m months? So let's use W for waste, M for months. Okay, so a landfill has 50,000 tons of waste in it. So that's how much waste we're starting with. So the amount of waste is 50,000 plus however much more we put in there. And each month it accumulates 420 more tons. So that would be 420 times the number of months that we want to go forward. Okay? So there's my function rule that represents the waste after m months, the waste after a certain number of months. Okay, let's look at another situation here. So here, going to a concert. Okay, so a concert seating plan is shown below. Reserve seating is sold out. Total revenue from ticket sales will depend on the number of general seating tickets sold. write a function rule that represents this situation. And what is the maximum possible total revenue? Okay, so we're gonna sell this out, right? We sell out the reserve seating. We could sell this out, and that is going to be where the maximum revenue occurs, is when we sell every ticket, obviously, right? If you sell the ticket, you sell at the seat or sell at the concert, and that's the total revenue. Okay, so let's make an equation for our basic revenue. Let's leave that up there. Okay, so total revenue is going to be the revenue from this area plus the revenue from that area. So revenue is going to equal to 25 times, well, there's 10 rows and 12 seats. So that's going to be, well, that's how much we're going to get for reserve seating, plus the revenue for general seating. So that's going to be, well, this one, we don't know how many tickets are going to be sold, so it's going to be 10 times n. Okay, so my total revenue is going to be 25 times 10 times 12 gives me 3,000, plus 10 times the number of general seating tickets sold. But if I want to sell out, I would have 30 times 16. So 10 times 30 times 16. So if I sold that out, I would get $4,800. Okay? So a sellout would give me $3,000 plus $4,800. Okay? Which would be the 30 to, that would be 160, no, not 160 tickets, 30 rows, 16 seats each. So it would be a 480 total seats in general seating. So if I sell them all for 10 bucks, right, that's my $4,800. And that would give me a total of $7,800 for a sellout. Okay, so here's my revenue equation based on how many seats I sell for my general admission, and here's how much money I would make in a sellout. Okay. Let's look at another situation. A kennel charges 15 bucks a day to board dogs. Upon arrival, each dog must have a flea bath that costs 12 bucks. Write a function rule for the total cost of n days of boarding plus a bath. We'll look at the second part in a second. So the first part is the cost, right? So let's call this cost is going to be 12 bucks plus $15 for n days. Okay. And then if I want to solve this for 10, it would be 12 bucks plus, let's go 15 times 10, which would be 150 plus 12 gives me $162. Does a 5-day stay cost half as much as a 10-day stay? Not quite. Close, but half of 162, half of 162 would be $81. Okay, but a 5-day stay is going to cost 12 plus 15 times 5. Okay, so yes, this charge right here, the daily charge, does go down by half, but my charge for the wash does not. So the cost of a 5-day stay is $87, not $81. So it doesn't cost half as much, almost half as much, but not quite. So both of those were actually linear functions, because as one variable went up, the other one went up the same amount. Let's see if we can make a function rule for a non-linear function. Okay, so let's write a function rule for the area of a rectangle whose length is 5 more than its width. So what's the area? Well, let's get to the second part in a second. So step one is let's first think about what this looks like. Here's my rectangle, okay? And the area of a rectangle, so hopefully you remember this, is length times width, okay? So we can't do much with this rule because it has two variables in it. So a better thing to do would be to put one in terms of the other. And that's what this sentence right here says, that whose length is equal to 5 more than the width. So the width plus 5. So instead of using the length right here, I can change that to the width plus 5. Okay. Now the area becomes width times the width plus 5. Okay. Which would be, if I multiply that together, that would be w squared plus 5w, if I distribute the w to both of them. And there's my function rule for this figure, w squared plus 5w. What's the area when the width is 9 feet? Not w, that the area, okay, so area is equal to 9 squared plus 5 times 9. 9 squared is 81 plus 45 to give me 126. Okay? So the area of the rectangle is 126 feet squared. Okay, because it's 9 feet. Area is in square units, feet squared. All right, let's look at one more got it problem, and let's see if we can make this situation. Okay, so the write a function rule for the area of a triangle whose height is 4 inches more than twice the length of its base. Okay. What is the area of the triangle when the length of the base is 16 inches? Okay, so let's see if we can get this. So let's first make a triangle. Okay. And we have a height and a base. And the area formula for a triangle is 1/2 the base times the height. Okay, but in this particular case, the height is equal to 4 more than twice the length of the base. So twice the length of the base plus 4. So the height, which is right there, would be 2b plus 4. So my area equation becomes 1/2 times b times 2b plus 4. Okay, so a little more complicated, but nothing that we can't handle. We could get a little fancy with this as well. Let's put it together first. So that's 1/2. If I multiply both of these by b, I would get 2b squared plus 4b. And then as I multiply the 1/2 inside there, I get b squared plus 2b. So my area formula is now b squared plus 2b. And the base is 16 inches. So the area is going to be 16 squared plus 2 times 16. Okay? 16 squared is 256 plus 32 gives me an area of 288 inches squared. Okay, so if I wanted to graph this, okay, function rule from problem 3, how do you know the rule is nonlinear? Okay, so I could plug in 1, I could plug in 2, 3, 4, 5, 6, 7. I could plug in all these things up, up to 16 and get a nice little graph here. But I will see that increasing the base inch by 1 is not going to increase the, well, let's do a couple real quick and I'll show you. Okay, so we have our base and our area as my input and my output. If the base is 0, the area is 0. Okay. If the base is 1, plugging it into my formula, don't forget my formula right here, b squared plus 2b. If I plug in 1 to that, I get 1 squared is 1, plus 2 times 1 is 2, so this would be 3. If I plug in 2, now we would get b squared is 4, plus 2 times 2 is 4, which would give me 8. Notice that here my increase is 3, but here my increase is 5. And watch again as I put a 3 in there, now that turns into 3 times 3, which is 9, plus 2 times 3 is 6, that's 15. So now my answer went up by 7. Okay, so each an increase of 1 unit on the base right here, of 1 inch on the base, is not increasing the same proportion, right? If it goes up by 3, then 5, then 7. Okay, so each increase in 1 is is increasing the next one by more and more and more and more. That's how we know the function is nonlinear. Okay, if we were to graph this, the graph would not be a line; it would be a curve. Okay. So my lesson check. Write a function rule to represent each situation. Okay, so first, C, total cost of C for P pounds of copper, and each pound costs $3.57. That's going to be that my cost is going to be equal to $3.57 times P. Height, F in feet of an object when you know the object's height in inches. So for this, height feet of an object when you know the object's height in inches. To feet, inches to feet, there's 12 inches in 1 foot. So the foot is going to be the height divided by 12. Okay. So the amount of your friend's allowance, if the amount she receives is 2 more than the amount X you receive. So her allowance is going to be yours plus $2. And finally, the volume of a cube-shaped box whose edge lengths are 1 inch greater than the diameter of the box of the ball that the box would hold. Okay. So to get volume is length times width times height. So if the edge of the box is the diameter plus 1, okay, 1 inch greater than the diameter, you just take that and multiply it 3 times. 1 length, width, height. 5, suppose you write an equation that gives A as a function of B. Which is the dependent variable and which is the independent variable? A would be the dependent. It would be the input. Okay. B would be the independent. Dependent A. B would be the input. That's the independent variable. Sorry. B input, A output. That's a function of B. B is the one that you're plugging in. A worker has dug 3 holes for a fence post. It will take 15 minutes to dig each additional hole. Your friend writes that this rule is 15 times n plus 3. Unfortunately, this is minutes, and this is the number of holes. Okay, so that is not right, right? For time in t minutes to dig and additional holes. It just takes 15 minutes times the number of holes you want to dig. That's it. Okay, so if it takes 15 minutes to dig each additional hole, just get rid of that. And that's how long it takes. It's a graph of a function rule that relates a square's area to its side length, continuous or discrete. So from last section. So if I want to graph a rule that relates the square's area to its length, I can pick any length I want. So my area can be anything that comes out of that function. So this is a continuous function. Okay. So that is 4-5, writing a function rule.